Hello grade 12s and welcome to question number 5 of the November 2021 Physical Science Paper 1 exam. This question deals with work, energy and power, and based on that you can see displayed to your screen the section from your formula sheet that is going to help you in this section. This is the section on work, energy and power. So if we have a quick look at this section of the formula sheet, you will see that we have the definition of work, or the formula that we can use to calculate work. I'd like to remind you that when we substitute values into this formula, we only substitute the magnitudes of the force and displacement. We don't include direction because the theta value takes the direction into consideration. Remember that theta is the angle between the force and the displacement of the object. Theta is not necessarily equal to the angle of an incline, so please be careful. See where your force is and compare its direction to that of the displacement. Then on the same formula sheet, you're going to see a formula that we can use to calculate the gravitational potential energy. Often in this video, you're going to hear me referring to this simply as just as potential energy, but please understand that I'm speaking specifically about the gravitational potential energy, the energy that an object has because of its height above the surface. Then we have the formula for kinetic energy. There is a formula which we call the work energy theorem. There's the work energy theorem in general. Then there's a formula that you can use to calculate power, and a formula that you can use to calculate average power when you know the average speed of an object. Now that we've gone through the formula sheet, let's take a look at question number 5. Question 5 says, a 2 kilogram block released from rest at point P, or is released from rest at point P, 5 meters above the ground. It slides down a frictionless curved track, PQ. See the diagram below. So on this diagram, we see the 5 meters. I'm going to label this as the height that the object will possess at point P. We know that at P, the box, is at rest, so its speed and velocity is going to be 0. There is no friction, so friction acting on the block here is going to be 0. And you're going to see in a moment that this means that we are welcome to use the principle of conservation of mechanical energy. Because remember, we can use the principle of conservation of mechanical energy in an isolated system, one where the non-conservative forces are not doing any work, and that is the case over here. Now, although they have not mentioned it, if we look a bit further, we can see that from Q, we can move 10 meters towards the right, and then we come to a point called point R. We see that this surface probably has friction, and that is implied by the fact that the surface is rough or drawn roughly. Then at the end of the track is a barrier which the box may or may not bump into. We will find out about that in a bit more detail in a moment. Let's start off now by looking at question number 5.1. Question 5.1 says, state the principle of conservation of mechanical energy in words. I'd like to remind you that mechanical energy is the sum of the gravitational potential energy and the kinetic energy of an object. We get different types of energies. We get light, heat, chemical energy, electrical energy. But the gravitational energy added to the kinetic energy of an object gives us the object's mechanical energy. The term conservation means we are keeping the mechanical energy constant. And on that note, the principle of conservation of mechanical energy in words states that the total mechanical energy in an isolated system remains constant, or we can say it remains the same. As you can see, there are sections of this statement that are underlined. That means that you're only going to get your 2 marks if you have written down those words or those parts of the statement. Now remember, the total mechanical energy is simply the sum of the kinetic and gravitational potential energies. So instead of writing out or stating the principle of conservation of mechanical energy as I first showed you, you can instead say that it is the sum of the kinetic and gravitational potential energies in an isolated system will remain constant. Right? It's exactly the same statement, but instead of using the words total mechanical energy, we expand on what the total mechanical energy is. Question number 5.2 says, use the principle of conservation of mechanical energy to calculate the speed of the box when it reaches point Q. Now, they do not necessarily need to tell us to use the principle of conservation of mechanical energy. They can simply refer to energy principles. But I would like to show you, in the previous question, they asked us to state this principle. The reason we do this, the reason we ask you to make these statements very often is because it is going to help you to perform the next calculation or maybe even the next calculations, right? So the fact that they asked us to state this principle sort of gives us this idea that we may need to use it, and that is in fact so. So we're going to start off by writing out the principle of conservation of mechanical energy. The principle of conservation of mechanical energy says that the sum of the potential energy plus the kinetic energy at point P, that is at the top of the incline, is going to be equal to the sum of the potential energy plus the sum of the kinetic energy at position Q. We can expand on this formula further as I have done, stating that the gravitational potential energy is equal to mgh and that the kinetic energy is equal to half mv squared. And we do this on both sides. Now we have been given the mass of the object, so we know the mass. G is a constant 9,8. At position P, you will remember that the height at position P is 5 meters. At position Q, the object will be on the ground. Therefore, the height at position Q is going to be 0. We know that the speed at position P is 0 because the object is at rest. So we can plug most of these values in. Let's plug in everything that we have. We have 2 multiplied by 9,8 multiplied by 5 plus half. The mass again is 2. We do know the speed at position P, that is 0. That's going to be equal to 2 times 9,8. The height at Q is 0 plus half mv squared of Q. Sorry, we do know the value of m, so I need to substitute that in. That is 2. Remember, the question asked us to calculate the speed of the box when it reaches point Q. So we are looking for the speed at point Q. And as you can see, we have currently a formula where we have substituted into the formula all of the values except this unknown that we are interested in. When we manipulate the formula, we find out that the speed of this box at position Q is going to be equal to 9,90 meters per second. And that is the answer to this question. Now, when we have the answer, when we write down the answer, we do not supply it with any direction. Because grade 12, we have calculated speed, and speed is a scalar quantity. So this is the final answer to the question. You're going to get your marks as follows. It is out of 3 marks. There will be 1 mark given for the formula, either the first version or the second version. 1 mark for the correct substitution everywhere into this formula. You are welcome to replace all of this and all of that with 0, because we know 0 multiplied by anything is just going to give us 0. And then we're going to get 1 mark for the final answer of 9,90 meters per second. Before we go on to question number 5.3, let's go back up to the diagram and add this value onto the diagram. we now know that at position Q, we know that the speed is going to equal to 9,90 meters per second. That is new information, and we're going to include it on our sketch. We so far looked at the motion from P to Q. Okay, that is one part of the motion. Do not try to look at everything all at once. We're done with the first section. Now we are moving on to the next part of the motion. There is new information given to us. They say the box passes point Q and moves 10 meters on a rough horizontal surface before striking a barrier at point R at a speed of 4 meters per second. We have new information now. So remember, we had the box, and I'm going to draw a little sketch to help us. We had the box at position Q. This box is now going to travel from position Q to position, or a position, that we are referring to as R. At R, there is a barrier, so I'm going to draw that barrier in as well using a red pen. We know that at position Q, the speed of this box is given as, or that we calculated it to be 9,90 meters per second. They have now given us new information. Firstly, we know that the length or the distance between points Q and R is 10 meters, so we're going to fill that in. Secondly, we know that when the box gets to position R, it will have a speed of 4 meters per second. So we're looking at the motion from Q to R, where the surface has or is rough, and therefore we know that this box is going to experience a friction force. Question 4.3 says, use energy principles to calculate the magnitude of the average frictional force acting on the box as it moves from Q to R. We are interested in finding the frictional force. The term or the word energy principles means that we must stick to the formulae that involve energy. So we must calculate the friction force by making use of either the work energy theorem or the work energy theorem in general. We may not, for example, make use of Newton's second law and the equations of motion, because if we do so, we're going to lose all of our marks. So we're not going to do the calculation that way. So I'm going to start off by writing out the work energy theorem. It is the net work is equal to the change in the kinetic energy of the object. In order to deal with the net work, we are interested in the net force acting on this box. So let's go to the diagram and let's include or write on this diagram all of the forces that are acting on block Q. It is also helpful to draw a free body diagram, so you're either going to draw yourself a free body diagram or you're going to draw directly onto the sketch provided to you on your question paper. So firstly, we know this object is on a surface and it will experience a normal force as a result of the surface. Then there's going to be the downwards Fg, because this object has mass. We're going to label this Fg. Lastly, we know that since there is friction on the surface, or since the surface is rough, there will be friction. Friction always acts in the opposite direction to the motion. So when we look at this diagram, we see that the normal force is perpendicular to the displacement of the object. Therefore, the normal force is not going to be doing any work. If we consider Fg, it is also perpendicular to the displacement, change in x, of the object. Therefore, Fg is also not doing any work. That means that the only force that is doing work is the friction force. And that means that the net work is done by the friction force alone. So we can expand on this equation and simply state that the net work is equal to the work done by friction, which is going to be the magnitude of the friction force multiplied by the magnitude of the displacement cos theta. We can expand on the part of the equation that deals with the object's change in kinetic energy, remembering that change always refers to the final value minus the initial value. And this is actually given to you on your formula sheet as I showed you at the beginning of this video. So let's go and substitute into this formula everything that we know. We do not know the friction force, that is what we're interested in. The magnitude of the displacement is 10. And as you can clearly see from the sketch, the angle between the friction force and the displacement is 180 degrees. So we say cos 180. This is going to be equal to the object's mass multiplied by its final velocity, which was given as 4 meters per second. Please do not forget to square your speed, or we can call it the velocity. The fact is, this value is going to be squared. So whether or not we include direction is not going to change the outcome. The initial velocity, or the initial speed, is 9.90 meters per second squared. So now that we've done or performed the substitution, we can manipulate the formula and we find out that the friction force is equal to 8.2 newtons. This is the final answer to this question. You're going to get marks as follows. Number 1, you're going to get a mark for substituting in the left-hand side of the formula. First you're going to get a mark for your formula in any form, so either the one right at the top or the second version. Number 2, you're going to get a mark for your substitution on the left-hand side, so the method that you would use to calculate the friction force. Then you're going to get a mark for your substitution into the right-hand side of the formula, where we calculate the change in kinetic energy, and your last mark will be awarded for calculating the frictional force to be 8.2 newtons. I would now like to show you how we can come to exactly the same conclusion, that the frictional force is 8.2 newtons, by making use of the work energy theorem in general. We call this the work energy theorem. The work energy theorem in general says that the work done by the non-conservative forces is equal to the object's change in kinetic energy plus its change in gravitational potential energy. Now, when we look at the object once again, we can see that there's only one force acting on the object and doing work on the object. It's not acting on the object, but there's only one force acting on the object that is doing work, and that is the friction force. So we know, since the friction force is a non-conservative force, we know that the work done by the non-conservative forces is equal to the work that is done by friction. So we can expand that part of the formula. The change in kinetic energy is exactly the same, half mv final squared minus half mv initial squared. The change in potential energy we're going to add, so we first write down a plus sign, and then we write down mgh final minus mgh initial. So this section over here, that is the change in kinetic energy, while this section is the change in potential energy. Now we can substitute into this formula. You're going to see we end up with exactly the same equation. It's friction multiplied by 10 cos 180. That does not change. Then we have half the 2 multiplied by 4 squared minus half 2 multiplied by 9.90 squared. We are then going to add the change in potential energy. Now the object's mass is 2. The gravitational acceleration's magnitude is 9.8. But what is its height above the ground in the end, and what is its height above the ground in the beginning? This object is moving on the ground. That means that the height at any point during this motion from Q to R is going to be 0. So we can substitute in the place of h the height of 0. We say minus 2 multiplied by 9.8 times again the height of 0. So what is essentially happening in grade 12 is that this section is going to disappear because everything there is 0. And we actually come back to exactly the same formula, this one over here. When we plug these values into our calculators and manipulate the formula, we come to the same conclusion, that the frictional force is equal to 8,2 newtons. But the main reason I worked through this different version with you is just to emphasize to you that if we are moving on the ground, if the object is moving on the ground, then the height throughout the motion is going to be 0, and we actually come back to the work energy theorem, the one that I wrote down right at the beginning. We now move on to the very last problem in this video, which starts off with new information. They say the barrier exerts an impulse of 14 Newton seconds to the left on the box when the box strikes the barrier, which means it hits the barrier. Impulse is the net force multiplied by the change in time, or the time itself. And we know, according to the momentum impulse theorem, that impulse is equal to an object's change in momentum. Impulse is a vector quantity, and that is why they tell us that the impulse is towards the left. That means that if we make any substitution into this formula, then we must take direction into consideration. Now they say calculate the change in kinetic energy of the box after striking the barrier. Change in kinetic energy is written like this, and of course we can expand on this formula by writing out half mv final squared minus half mv initial squared, right? So that is what we're trying to calculate. But before we perform this calculation, let's try to understand exactly what is going on. The box just moved from point Q to point R. It's going to strike the barrier with a speed. Its speed is going to be equal to this value of 4 meters per second that was given to us, because in the previous question they said it's going to strike the barrier at a speed of 4 meters per second. So we know the speed with which it's going to strike the barrier is 4 meters per second. When it strikes the barrier, it's going to experience a force and therefore an impulse. There is a collision that takes place. The impulse over here, we know, is going to be equal to 14 Newton seconds, and we have not yet decided on a direction, so I'm going to leave it as its magnitude of 14. After this collision takes place, we need to know in which direction the object is going to move, or will it move at all? Because if we look at the formula for calculating the change in kinetic energy, then we need the mass, which we have. We need the initial speed or velocity, which we have as 4 meters per second, but we are missing the value or the final velocity. We don't know what the final speed of the object is going to be after striking the barrier. So please understand, we have moved past this section of the motion. First, we dealt with the section of the box moving from P to Q. Then we dealt with the motion from Q to R. And now we are dealing with the collision with the barrier. So there are 3 sections, 3 different parts of motion that this question deals with. So since we need to calculate the final speed or velocity, we can make use of the value of impulse that has been given to us. We know impulse is the net force multiplied by change in time, which is equal to the change in momentum. Change in momentum is mv final minus mv initial. We know the impulse, right? So we know the value of the impulse was given to us as 14, but we need to choose at least one direction, or one direction to be positive. So let's go and choose towards the right as positive. You're welcome to choose towards the left as positive. If we choose towards the right as positive, then it means that the initial velocity is positive, but the impulse is going to be negative since the impulse is towards the left. So into the section of the formula that is impulse, we're going to substitute in negative 14. That is going to equal to the object's mass, We do not know the final speed, that is what we're interested in, multiplied by 2, the object's initial, sorry, I said speed, but I was supposed to say velocity. The object's initial velocity is 4. When we manipulate this formula, we find out that the final velocity of the object after it hits the barrier is going to equal to negative 3 meters per second. That is its velocity. So that means that after hitting the barrier, the object is going to move at 3 meters per second towards the left. That is what is going to happen. So now we have all of the information that we need to calculate the change in kinetic energy. So we can substitute values into this formula. We have half the mass of the object multiplied by, I'm going to substitute negative 3 into this formula. You can substitute into this formula either the speed or the or the velocity with its direction. And the reason I say so is because the negative is not going to change anything because it is being squared and ultimately will become a positive value. So if you only substitute the magnitude of 3 into the formula, you're going to get the correct answer. We say minus half the mass again, and the initial speed was 4. So we plug that in. Into our calculators this goes, and the final answer that we obtain is negative 7 joules, where we leave the answer as negative because we know, and when we deal with the section on energy, then negative does not imply direction. Negative speaks of whether energy has been gained or lost. So we leave the answer as it is with the correct SI unit with it, which is joules. And grade 12, this brings us to the end of this problem, which is actually the last problem in question number 5. The marks will be awarded as follows. Number 1, you're going to get a mark for your impulse momentum theorem, for writing that formula down. Then you're going to get a mark for substituting into that formula. Of course, you had to take direction into consideration. You then get a mark for writing down the formula to calculate the change in kinetic energy. 1 mark for substituting into this formula. And lastly, a mark for your final answer to this question. That gives you your 5 marks for question 5.4. This entire question is out of 14 marks. Grade 12, this brings us to the end of this video on question number 5, which dealt with work, energy, and power. In the next video, we will look at question number 6, which will deal with the Doppler effect and red and blue shifts.